equation, this is 4.44, I believe. And I'm not going to say a whole lot about it, just that there on page 106, page 105 and 106, I'm going to just mention this and leave it behind, but the author does a derivation to get down to this equation that the partial, and this should be delta G, the partial of the change in the free Gibbs energy divided by temperature over the partial of 1 over T, and you think, boy, why would anybody ever be interested in that relationship? Seems pretty complicated, but there is an interest in it only because that relationship is equivalent to delta H. All right, so, and he derives that down through there. And I think one of your homework problems asks you to do something with that. But oh yeah, one of your homework problems is based on that equation.
Is it from this homework? Or?
Yeah, chapter 4 homework. So take out your calculators, because we're going to actually start out with a calculation. I'm going to do a little bit of, put a few other equations up here and do another calculation or two, etc. And get through those 4 topics, and that'll pretty much end chapter 4. Grant asked a question about the Joule-Thomson coefficient, which is also in this chapter, and we haven't touched on a lot. What you're going to see are some of these things that get introduced like this. We're going to just kind of define what that is and do one calculation based on it and then kind of leave it behind. But in chapter 5, we're going to get back to that. Okay, so in some cases we're just being introduced to something and then it comes back in. Like compressibility. Compressibility was introduced in chapter 1. And it comes back in here in chapter 4 when we start talking about fugacity. Okay? I was thinking about this. It's a little bit like a spider web. You know, a real big spider web. And you come over here and you tug on this little part of the web, and it has an effect over here. Everything is, these things are all connected. I forget whether it was Liz or Taja that asked the question, how can we, we're talking here about internal energy, and there's all we've been dealing with is enthalpy, and how can we calculate the internal energy when this is all that's changing there? And we see they're related. All of these things they're interrelated at certain points. Well, just to start out and warm you guys up, think about this question and work together if you want to. This is not hard, but crunch down through here and answer this question. Determine the temperature beyond which this process is spontaneous. We're looking at calcium carbonate, solid calcium carbonate, crystalline calcium carbonate. And what temperature would that occur spontaneously, where it would decompose into calcium oxide and carbon dioxide gas? What's the condition for spontaneity? Delta G. Yeah, okay. Okay, delta G equals 0, it would be at equilibrium.
These delta H values, they're standard delta H values at like at a certain temperature. So does delta H, is it ever a function of temperature, or is it always constant? You know what I'm saying? Like, can we use standard?
Yeah, we can use standard. Delta G naught has to be less than or equal to 0. So if we would have delta H minus T delta S is less than 0. So delta H equals, not equals, is less than T delta S. So delta H divided by delta S is less than T, or if T is greater than that, if T is greater than that, it's going to be spontaneous, right? And so what is that T?
1,108 Kelvin.
Okay, so if the temperature goes above 1,108 Kelvin, that will occur spontaneously. It'll decompose calcium oxide. One thing that struck me as I was going down through this, when you take water with calcium carbonate in it and you boil it, what happens? When you heat up and boil that water, now that's at 100 degrees centigrade. So at 100 degrees centigrade,
We're still not there.
if you have calcium ions and carbonate ions floating around in here, take it up to the boiling point of water, you can drive off carbon dioxide. And you get calcium oxide. The carbonate that decomposes the CO2, you get calcium oxide, and I guess you get calcium bicarbonate, things of that nature, but you can get this. But we won't dive into that. But what I'm saying, in solution at a much lower temperature, you can kind of drive this reaction. But this is crystalline calcium carbonate. So this would predict is pretty stable.
So yeah, I guess I'm confused on that. So if it's at 100 degrees C, that's 373.
Yeah. Okay.
Kelvin.
Okay.
So the
Okay.
reaction is not spontaneous in water, right? I guess so. How would you think about the breakdown there? Is it still producing ions, or would you say that it's not producing one?
Well,
It's at 100 degrees C? Or is it producing some? I mean, how that's related to K, the equilibrium constant.
Yeah, thank you for correcting me. I was in 100 degrees centigrade, 373 K, but still, third that temperature, at that temperature you
It's
can
somewhere
get
else.
this, you can get this reaction to occur.
Calcium carbonate dissolves in water. Does it?
Not real well,
Okay.
like about 150 parts per million, something like that. So it's not, doesn't readily.
Yeah.
But even if you had a chunk of it down in here, I think eventually
You could get it all to funnel
you could
out.
get it all to
Yeah.
get out and end up being calcium oxide by this. And that would be spontaneous in water at that temperature, but in crystal, it's a whole lot more.
Oh, because that was like nice.
Here's,
Solid of gas.
again, we're in centigrade here, but I put the 1108 in here. So crystalline, 100 degrees, 200, 300, 400, etc., nothing's happening. The crystals are very, very extremely stable. There's no activity, but you get to about 700 degrees centigrade, and then you would start seeing some CO2 coming off, and you would get it at 1 atmosphere at that point in time, at 1108. That's where it would be happening spontaneously. Okay, before we go into the next problem, again, I gave you that sheet on Monday, and we went from these basic equations to the Maxwell relationships and got them into things. Probably good to either have that sheet and have a scratch sheet of paper, and when you're seeing some of these partial differentials, is just kind of work from here and develop it back to there. For example, you can get to the partial of G with respect to pressure at constant temperature is equal to what? Okay, so if we set dt equals 0, and we take the partial G with respect to pressure at, so we'd have the partial of V dP with respect to dP. All right, what does that? This is going to go away. Volume, so that's going to just be equal to V. I'm sorry, I got those back up. I keep doing my dP. I'm a little backwards on that. Okay, so the partial G with respect to pressure at temperature is equal to the volume. So dG at this constant temperature is equal to V times dP. Delta G equals, if you integrate this from Pi to Pf, V dP, it's V times Pi to Pf well, let's see. We can replace V with what? If we're talking about an ideal gas?
nRT over P.
Okay, nRT over P. So we got nRT over P dP. So that is equal to nRT dP over P. All right, which then becomes just nRT, the log of P final over P initial. All right, that's just coming from the integral. If you integrate 1 over x dx, it's going to equal the log the log of x.
So is this a new equation? You say?
No, the
So you could
not
say
a new
delta
one.
G at constant time equals that, right? That's the
yeah. And that is equation 4.45.
So we have in the previous chapter we were given that entropy is equal to negative. Never mind.
Entropy.
Never mind. I was looking. I missed the temperature in that one.
Okay, so this is delta G, and we're leaning heavy on delta G because, well, that's going to move on in here to chemical potential and equilibrium, constant temperature and pressure conditions. That's going to be really related to chemical systems very well. So we have that equation. Delta G equals nRT times the log of the natural log of the final pressure over the initial pressure. Okay, so right down below there, right down below here somewhere, next slide, I think it is. You have this problem. Okay, so we just had this equation. So we start with that equation. Like I said, it's 4.45. And solve that problem. We got 0.988 moles of argon. It's expanding, so here's VI, 25 liters to 35 liters at a constant temperature, 350 K. Calculate delta G for this expansion. All right, equation 445 doesn't say anything about volume, but PF equals what? Assume an ideal behavior.
nRT over VF.
Right. And PI equals nRT over VI. Okay, take it from there. Calculate.
Can't you just put a negative sign in front of the equation and change them to volumes, like we did for that reversible work? I mean,
Yeah,
it's probably doing the same thing, actually.
Yeah, there's two ways of doing it. There's that way of doing it, or I mean, if you just plug it into that equation.
Oh, like the delta G equation, if you make that negative, it works for...
If you make it
volume.
negative and put volumes in,
Yeah.
it should be the same thing,
Yeah.
I think.
Or if you, yeah, I think that is right. It would be, this would be right. VF over VI. Or if you just plug into that equation, what you're going to get is nRT ln VI over VF. The volumes are going to just be the inverse of what they are. So mathematically, same. I guess whatever you prefer, but I just substituted these things into there. Okay, Ryan. We'll see you.
No.
anybody sees Ryan, tell him we'll start chapter 5 on Friday.
Okay, I'll call him in like an hour.
All right.
Do you have a presentation or something?
He has
Yes.
a mock interview.
Oh.
Whatever it's called. I guess it was the only time I could do it.
What did you guys get?
I got negative 0.0272.
In, what's your units?
I did not do units because I was lazy. And I
Did you get it in the negative 900s?
Did you do the
Wait,
volume or
you
did
final?
you do the pressure?
Expansion. I did volumes. It's 35 liters.
I did
25 to 35.
Because it's final or initial, yeah.
Where did I do this?
Okay.
Wait, what are you?
Well, so if we're talking delta G, we should use the R value of joules per mole per Kelvin,
Yep,
I think. Right.
that makes sense.
And then we don't really care about our volume units because it's a ratio and it's the natural log of it.
Alright, what'd you get?
Got a different number this time.
117.8 joules.
No, I
Got a
got.
different number than that.
What'd you get?
Negative 2800.
I got negative 965.
Oh, I know why.
You all got different numbers?
I got negative 967 again.
This might maybe the
I don't think the volume. Did you do volume grant or did you?
I used volume.
I used pressure.
Oh, well, we're off that point I
So you calculated pressures?
Negative 965.
Yeah, she used pressure.
You calculated pressures?
Yes.
Okay. Yeah, that's probably more work than you need to do. You just stay with the volumes.
Yeah.
Oh, wait,
But I mean, you can do it.
I think I plugged in my calculator on.
Yeah, that's what I have.
Yes, 967. Sorry, I caused a lot of confusion.
All good.
Taja, you getting there?
Yeah, I'm gonna do the volume.
Anybody need any light?
Oh, I like it like this.
That's
35.
Well, a little bit. You like it like this?
Well,
Yeah.
is if people like
I got
feel like they're
some.
dark and then someone turns on the lights and it's like blinded and then you have
Okay.
to adjust for a few minutes.
Taja, what'd you get?
Negative 965.35.
Okay.
967, sorry. Negative 967.
And that's joules, right?
Yes.
Joules. Because this is joules per mole Kelvin. 8.3144 joules per mole Kelvin. And then we got moles crossing out, Kelvins crossing out, we got joules. All right. Okay, we're just stepping through a couple things here to finish up this chapter. Let's go on. Chemical potential. These things kind of work out better to write them right on the board, but I'm trying to see how well I can write on this tablet right here.
Are there any conditions, like you can only use that equation that you gave us for adiabatic or isothermal, or is that pretty universal?
Well,
It's
that's
gotta It's gotta be isothermal.
It needs to be
because
isothermal.
temperature.
Yeah. Yeah. Okay, now this has a definition. Oh, but the thing to keep in mind as we segue on into chemical potential, everything we've been doing, delta H's, delta U's, delta S, talking about Gibbs free energy, we have talked about it in terms of the amount of the material held constant. We've talked about holding temperature constant, isothermal, but pressure and volume might be changing, and holding pressure constant, temperature and volume might be changing, etc. But in all of those cases, the material, the amount of material has not been changing. We haven't dealt with that yet, any change in material. The system, we talked about an ideal gas, the amount of gas has stayed constant. Even when we talked about the entropy change, when you mix two gases together, we we talked about a certain amount of each of those gases separate from one another, and then those same amounts mixed together. That's the closest we got to a change in amount, but we didn't even have a change in amount there. The amount stayed the same, they just mixed with each other. And what happened to entropy? So now we're going to move on here. We could do this with all of the energies, the internal, the Helmholtz, the enthalpy, but we will focus almost exclusively on the Gibbs free energy. And so there's a definition, really, the change in Gibbs free energy with respect to the amount of material at constant temperature and pressure. So that is how this chemical potential is defined. The change in Gibbs free energy with respect to the moles or amount, constant temperature and pressure. All right, and if we had a number of different things in our system, then we could be talking about the chemical potential of any one of those.
Did you say that mu is that fugacity coefficient?
Is what?
Is that the fugacity coefficient? No, that's
No.
the circle.
No, that's different. They're going to be related, or we're going to link them together. But this is a fundamental parameter here, chemical potential, and it's independent of fugacity at this point in
So
time.
mu is chemical potential.
Yeah, that is chemical potential. Chemical potential is defined as the change in the Gibbs free energy with respect to the amount of material at constant temperature and pressure. And so we could have, with respect to any particular component of the system, a particular component of the system, its chemical potential would be the change in the Gibbs free energy with respect to a change in the amount of that material at constant temperature, pressure, and all other materials. NJs.
It's just for multiple gases.
Gases, eventually will expand into just multiple materials, whether solids, liquids, or gases. All right, so if we took that and wanted to get kind of the full differential of Gibbs free energy, we'd take the partial of G with respect to T, these things that we're holding constant right here. Now we'd keep all of these things constant, dt plus the partial of G with respect to pressure at constant temperature and material, plus the sum of the partial of these G's with respect to the change in the amount of any particular material, constant temperature, pressure, and all the other components in the mixture or in the system. And you get that equation.
So what did we just do to get that?
Well, we're taking the total differential of this for Gibbs free energy for kind of this system. So what I'm doing, I'm taking the partial G with respect G, this.
Okay, then with respect to P,
Holding these others constant
okay.
with the change in temperature, plus the partial G with respect to P, holding temperature and these components, plus summing up all of these
Other gases.
chemical potentials. All right? And this is equal to, I mean, it doesn't surprise us, it shouldn't, that is the negative of the entropy. This is volume. So that's what we had before we started thinking about even a change in the amount of the materials in the system, plus this sum, and this here is the chemical potential for component Ni. So this is going to be chemical potential times the change in the amount of Ni. All right, and this is given the title, a kind of a summary, the fundamental equation of chemical thermodynamics. Because as we get in now, as we move on into chemical systems, we're going to be seeing the components of the system changing. Hydrogen and oxygen becoming water. The molar quantities of those three things are going to be changing. You have three different components in your system. And so that's going to end up being a critical part of this. And so this is an equation that now encompasses all of the, every aspect for this state variable. This is really a function of temperature and pressure, and now the change in material.
So in this case, mu I, like the sum of mu I, how would you calculate that, I guess? So you're saying there's three different things in the system, and there are changes in moles, or I guess I'm kind of confused on just the last term, like what?
Well, this could let's say you had two things in there, so you'd have mu1 times the change in the amount of component 1 plus mu2, the chemical activity, the chemical potential of component 2 times the change in the amount of that.
Right. So we can have multiple, like,
yeah, some.
That's for each one. Okay.
Yeah, from I up to however many there are.
Yeah.
Okay, but okay, how do we calculate? Let's try to get to a point where we can at least do one calculation on chemical potential. Let's go back to equation 4.45, and we have that delta G equals nRT over the log of the final pressure over the initial pressure. And so let's take this and divide it by n. Delta G over n equals RT ln PF over PI. And this delta G over the amount of n is basically the chemical potential. So we get to that relationship. We get n out of that equation. chemical potential equals RT times the natural log of the final pressure over the initial pressure. And this is equation 4.54 in your book.
This is at constant temperature.
Yeah, at a particular temperature. So let's move on to the next problem. And let's use that equation. So we're using this equation.
So, does work then equal delta G for isothermal? Because that equation is identical to what we used previously.
When we were looking at internal energy,
Yeah.
and we had RT times the log of the...
We had nRT times log of P final over P initial.
Yeah, so, yeah, that would suggest there's a very close relationship to that and the...
Adiabatic only, correct?
That's for isothermal.
Is it
Just for
isothermal,
isothermal.
work reversible? Does it
Reversible.
matter if it's
Reversible.
adiabatic or not?
I don't think it had to be adiabatic.
Does adiabatic give a temperature change?
Yeah. You should.
Oh, I see. Yeah. So, because if you guys have looked at 4.16, you need to find a way to relate work and delta G. So I think this might be the way. So I've been trying to figure out how to do it, but
Yeah, so that observation's a good one.
yeah.
Okay. Okay, well, let's go on and do this problem. Calculate the molar change in chemical potential of an ideal gas that expands by 10 times its original volume at 100 K and 300 K.
That's true.
Grant, what equation, do you know what equation that was? Do you have an equation?
I don't know the geometry of that one.
Probably, what chapter?
Yeah, that would be equation 2.7.
2.7. Yeah, 2.7, 2.8. Both of those, I guess.
Say we measure chemical potential in joules.
But this is molar, so you should have chose for mole. Because that equation you gave us didn't have N in it. 454. So that's per mole. So that's
Wait, so
Yeah, so-
what we're calculating is per mole, is that?
Well, you could, Grant, you could put 1 mole in front of this, too.
Well, yeah, you could, but
Yeah.
it asks for the molar change.
Yeah, I see.
So.
So this is actually going to end up being VI over VF, right?
Okay, do that. VF over VI, and put a negative in front of it.
Expands, so the final volume is 10 times the original volume.
There's no chance. Yeah, that's
19 and 57.
where is education? You have joules per mole.
So what are we getting?
Like 19 and something.
Yeah.
19, 14, and 57, 43.
I got negative. Is it negative possible?
I had PF or PI, so.
But we are
It's volume.
volume.
So it's
Oh, we're using.
So you either need to put a negative in front and use VF over VI, or switch them around.
Wow.
I
don't know.
changed mine for you. Peer pressure. That's why I'm motivated.
And B is what?
Oh, B is-
Negative 57, 43.
Yep.
Is that joules per mole or just joules?
Look at your ideal gas constant. Your ideal gas
Yeah,
constant
five
is joules per
mole.
mole K, and then your temperature.
You don't have
Yeah, so the molar change, I guess it would be joules per mole would not be incorrect. That's how many joules it is per mole. Okay, let's just go from that equation a little bit further and see and get to fugacity. We won't go through all the steps, but it is going from chemical potential to fugacity. And fugacity is going to come up again in chapter 6 or 7. There's a relationship between chemical potential, fugacity, and another concept that'll come in, I think, in the next chapter, activity. And maybe, why is this introduced? I think fugacity is introduced at this point. It was introduced in like 1920s, brought in. We've talked a lot about ideal gases. We keep falling back to ideal gases as kind of our standard fundamental point of stepping off. But fugacity is an attempt now to go from ideal to real a little bit more. So this fugacity is introduced. So let's just go through a few things here, and these are in the book basically, but it says delta G we could basically talk about as our G final minus our G initial. So delta G is equal to nRT times the log of the final pressure over the initial pressure. So basically the final Gibbs free energy minus the initial is equal to this nRT times the log PF over PI. Now if we say, okay, let's consider standard conditions, and so at standard conditions then delta GI is delta G naught, and PI would be standard pressure. Okay, so if we did all that and just substituted delta G naught for GI and dropped these final initial kinds of things, we would have that G minus delta G naught equals nRT times the log of the pressure over standard pressure. Or Gibbs free energy is the delta G naught plus nRT ln P over P naught. Okay? Not doing a whole lot there. We're just taking that delta G equals that, Well, delta G is the final minus the initial. So that rearranges to here. We get rid of all these subscripts and we have that equation. I didn't write the equation number.
This is to calculate delta G at non-standard conditions? Or
Yeah, G at some other condition.
okay.
Right. You got a new pressure. You got standard pressure.
Yeah, and you have a new temperature. Correct. Or-
Yeah, new temperature, and you still have your standard Gibbs free energy.
Okay.
So now we could do a similar thing with the change in chemical potential. It's going to be the final minus the initial. And same thing here at standard conditions.
If you say standard conditions, that's 0.
No, I mean 25 degrees C.
Okay.
And so 25 degrees C, 298 Kelvin.
What was it?
Well, 298 Kelvin and 1 atmosphere.
Standard pressure temp.
STP is standard temperature and pressure. Standard conditions would be standard conditions for the calculation of Gibbs free energies and enthalpies and entropies. So yeah, kind of move away from the gas laws. And when we're in the gas laws, we use STP to compare one gas to another gas. But to compare one material to another material, we're not at STP, we're at these standard temperature, this 298 and 1 atmosphere, which is the temperature at which these things are experimentally determined. Okay? So here, delta, or mu I is equal to mu naught, and again, Pi is equal to P naught. And remember, mu is RT times the log of PF over PI. So we end up with this mu minus mu naught is equal to RT times the log of P over P naught. So mu, chemical potential, is equal to mu naught plus RT ln P over P naught. Okay, when we get down to this point right here, just talking kind of more or less ideal gases, and they introduce, here's where fugacity is introduced. Fugacity. And F is equal to a fugacity coefficient times pressure. And if the gas is ideal, if it is an ideal gas, the fugacity coefficient is 1, and fugacity is pressure. There's no difference between the actual pressure and the pressure of that gas. It's an ideal gas. It's behaving ideally. So for ideality, the F is the fugacity and phi is the fugacity coefficient. And this equation then gets rendered just this way: RT times the log of the fugacity divided by the standard pressure.
And that is for non-ideal gases, right?
Basically for all gases, but it's
specific
used to accommodate non-ideal gases.
Because we couldn't use the top one. Could we? Could we use the top one for ideal? I guess.
We're presuming ideal behavior. all the way down to this point. And so now we're
Until here, right? Yeah.
until here. And so now we're saying, okay, how can we deal with it if it isn't ideal? And let me just scratch out a couple more things and get you down to your final equation. Just looking for the equation number. Yeah, 461. We want to get there. But to get there, they developed this, the chemical activity minus the chemical activity of an ideal gas is going to equal this mu naught plus RT ln F over P naught. Okay, so far that is that. That's your chemical activity of your real gas. And if you were to see the difference between that and an ideal gas, then you'd have this plus RT times the log of, for the ideal gas, like I said, this is 1, so the fugacity, the pressure is P. There's no difference. These things are crossing out of here.
Should there be an equal sign between there? You just have one line. Just want to make sure that's not subtraction.
I think. What?
No, that's a minus.
Oh, it is.
See, this here is this, and this here is this.
Oh, okay.
So it is a minus. It's not an equal sign. It is a minus. And so what we're getting is that this mu minus mu ideal equals, if you bring RT out in front, you got RT times the ln of F over P naught minus the ln of P over P naught. That's going to equal RT times the natural log of F divided by P naught over P divided by P naught. Let's see, how can we get that? All right, so we're minus these. If we want to add these together, we could invert those, and we'd have F over P naught, P over P naught. And that ends up being, these are crossing out, RT times ln of F over P. So the difference between your chemical activity, chemical potential of your real gas compared to the ideal gas is this, RT over the log of the fugacity over the pressure. That's not standard pressure. Whatever the difference between those pressures are.
That equals delta mu, or right, or change in mu minus mu ideal.
Yeah. And so you end up with this being, remember, F equals phi times pressure, so F over P equals phi. Right? So that's how I'm going there. So the natural log of that is going to equal, and I'm not going to go into all this derivation, but it gets down to, this is how you get to this point. And this is equation 4.61. So the ln of phi, this fugacity coefficient, is equal to okay, I was going to have you do this calculation, but you got that equation? I'll write it again, just a second. Here's this. Calculate the fugacity of 100 atmospheres of argon gas at 600 K, assuming its compressibility is adequately represented by the truncated viral equation Z equals 1 plus B prime P over RT. So you got that expression right there. And it's giving you what the B prime is here. Comment on the answer. Calculate the fugacity. Now remember, fugacity is F. All right, well, let's just walk down through it real quickly. So the ln of phi equals and this is, you can go right in, this is example 413 in the book. So you have a pressure going from 0 to 100 atmospheres. Here's this, this compressibility right here. Now remember, it's going to be Z minus 1. So that's Z minus 1. So 1 minus 1 is 0. So this reduces to just B prime P over RT. You integrate that from 0 to 100. You get this set up here. Substitute all this into there. So remember, this log of the fugacity coefficient is equal to this. You get an answer of 0.024. You take the analog of that. So ln of phi equals that. Phi equals that. Since fugacity equals phi times p, this means that the fugacity is 102 atmospheres. P is 100 atmospheres. So this times 100 gives you that, 102 atmospheres. Is that the pressure? No, the pressure is 100 atmospheres. But this real gas is appearing that under these conditions it would exert 102 atmospheres of pressure. It's off that much from what an ideal gas would. Okay. Look over that example, that equation, that example, calculating that. That's the last of chapter 4. Read the summary, chapter 4.
Could we maybe like review how, like maybe next time, or how
Well,
to, like evaluate integral? I guess I'm just like calculus.
Yeah.
I mean, I'll look at it.
Yeah, why did we not get to logs there?
Yeah. So if we can like
Yeah, okay.
explain maybe next time how you like do that evaluating the integral and getting it.
Okay.
From it.
See it.
Thank you.
Yeah, you're welcome.
About one of them from the book.